On January 5, 1945, an irreversible threshold was crossed during carrier qualification operations. A routine training flight ended in a total loss when an aircraft struck the deck edge of a converted training vessel. The operational objective for modern recovery teams was strict. They needed to locate, legally extract, and preserve a sunken World War II military aircraft for public curation without inflicting surface-level wave damage during the lift. This is the forensic investigation and recovery of a Grumman F6F-3 Hellcat, Bureau number 25910. This specific airframe was not a standard training asset built solely for domestic use. Bureau number 25910 entered fleet service in 1943. It was assigned to Fighting Squadron 38, operating as a land-based Navy fighter unit. The aircraft completed 3 full combat tours during the Solomon Islands campaign. It logged extensive operational hours operating over Guadalcanal, New Georgia, and Bougainville. In September 1943, this Hellcat took part in a protective escort for an aircraft carrying Vice Admiral William F. Balboa Halsey. The operational demands of the Solomon Islands campaign subjected the airframe to extreme structural loading during combat maneuvers and unimproved runway operations. Despite these environmental stresses, the high-mileage combat veteran survived the intensive operational tempo and mechanical wear of the Pacific Theater before being rotated back to the United States for secondary duties. Following its frontline service, the aircraft was reassigned to the Carrier Qualification Training Unit based at Naval Air Station Glenview in Illinois. The operational parameters shifted from combat patrols to repetitive carrier landing cycles on Lake Michigan. The environment provided a secure area for pilots to train on sidewheel passenger steamers converted into freshwater training carriers. On January 5th of 1945, Lieutenant Junior Grade Walter B. Elcock approached the training carrier. The approach was too low. The aircraft dropped its starboard wing and struck the deck edge. The Hellcat hung off the deck by its tailhook for several minutes before falling into the lake. The pilot safely escaped the sinking aircraft, leaving the structural condition of the submerged airframe as the primary variable for future investigators. The airframe sank to the bottom of the lake, establishing a strict set of forensic and structural parameters. In cold freshwater, chloride-driven corrosion and high conductivity attack were reduced rather than eliminated, preserving enough wartime structure and surface evidence to make recovery plausible. For engineers, that preservation changed the planning baseline. The Hellcat did not have to be treated like a collapsing ocean wreck, but the team still had to verify its exact configuration with remote sensors before any physical intervention could be authorized. The environmental record made recovery plausible, but the crash sequence still had to explain why an airframe built for carrier landings failed at the deck edge, and why that same failure helped preserve it. A standard open water ditching transfers extreme kinetic energy directly into an airframe, typically tearing the engine from its mounts and collapsing the forward fuselage. The physical geometry of a deck edge strike rewrites this destruction sequence. The operational hazard of carrier qualification training requires pilots to land heavy fighter aircraft on a compact moving target. The structural load paths of a heavy naval fighter are engineered to absorb the severe vertical forces of a standard centerline carrier trap. However, an asymmetrical deck strike introduces lateral and torsional loads that the airframe is not designed to withstand. During the final approach to the training vessel, the aircraft descended below the mandated glide path. The starboard wing dropped, causing it to strike the physical boundary of the flight deck. This collision bypassed the reinforced landing gear entirely. The asymmetric drag interrupted the forward momentum of the aircraft, forcing it to skid outward toward the perimeter rather than rolling down the center line. As the aircraft slid off the deck edge, a localized geometry constraint prevented total airframe destruction. The extended tailhook snagged an arresting wire at the boundary of the flight deck, shifting the load path and suspending the aircraft instead of allowing an immediate high-speed water impact. Held there for several minutes, the Hellcat shed its forward kinetic energy into the ship structure rather than the lake surface. This temporary structural suspension created the operational window the pilot needed. Institutional protocols for overwater emergencies demanded rapid egress, but the forces of a live crash sequence usually restrict escape. Elcock used the pause to get clear before the aircraft reached the water. When the tailhook and wire geometry finally slipped free, the Hellcat fell far closer to vertical descent than a normal high-speed ditching, reducing the impact loads that would otherwise have torn open the wing roots and forward fuselage. Once the aircraft slipped beneath the surface, it began a rapid descent through the water column. The dense mass of the forward radial engine dictated a nose-down trajectory. The internal fuel tanks and cockpit compartments flooded immediately. This rapid fluid intake reduced pressure differences across enclosed spaces as the aircraft descended, limiting the stress on hollow compartments in the wings and fuselage. The aircraft sank to a final resting depth of 250 feet. At a depth of 250 feet, the ambient environment is extremely dim, cold, and far more stable than the surface layer. Upon reaching the bottom, the aircraft impacted a thick layer of silt and mud. The soft composition of the lake bed distributed the deceleration forces across the entire lower surface of the aircraft. This prevented localized crushing of the lower fuselage and wing sections. The mud immediately enveloped the lower extremities of the wreckage, burying the landing gear and lower engine cowling. This deep sediment layer effectively sealed the lower sections from further physical disturbance. That intact condition now turned the investigation from crash mechanics to search geometry. How do search teams isolate a single acoustic shadow buried under 6 decades of accumulated mud? Searching a massive flat lake bed for a localized aluminum target required first narrowing the water into a defensible survey zone. Standard global positioning data did not exist when the aircraft went down, so A&T Recovery rebuilt the day of the loss from institutional archives, carrier steaming paths, wind headings for flight deck operations, weather information, and the recorded time of the accident. Those records converted an open lake into a measurable sonar polygon, eliminating hundreds of square miles of empty water from the operational plan. With the surface grid established, the operational focus shifted below the surface. At 250 feet, limited visibility and suspended particulates made cameras useful for confirmation, not for wide-area search. The team deployed side-scan sonar arrays to sweep the designated grid methodically. The sonar towfish operates by emitting acoustic pulses laterally across the lake bed and recording the return echoes. The survey vessel tows the sensor back and forth in overlapping lanes, ensuring no blind spots remain between the swept paths. Hard surfaces reflect sound waves strongly, while the soft mud bottom absorbs the acoustic energy. The acoustic returns generate a topographical map of the bottom, but the mud creates a discrimination problem. A partially buried aluminum airframe can lose much of its recognizable outline in direct reflection, making it easy to confuse with boulders or other debris. Operators therefore focus on the acoustic shadow cast behind the object rather than the return from the object itself. The length, density, and geometry of the acoustic shadow provide measurable data about the height and shape of the target protruding from the mud. A natural rock formation casts an irregular shadow, while an intact aircraft casts a shadow displaying distinct right angles, straight wing edges, and a vertical tail profile. An acoustic shadow resembling the exact wingspan and fuselage dimensions of a fighter aircraft confirm the presence of a structural anomaly within the reconstructed search grid. A localized inspection pass verified the target dimensions matched the specific aircraft parameters. The operational phase of localization was complete. Identifying the target in the mud solves the sensor problem. But how do engineers break the mud suction without subjecting the fragile aluminum to uncontrolled ascent? Extracting fragile aluminum from a depth of 250 feet introduced a severe mechanical paradox. The silt that had protected the lower airframe now acted as a suction load, anchoring the landing gear and engine cowling into the lake bed. The recovery team had to generate enough upward force to break that hold while strictly controlling acceleration the moment the seal released. Using a traditional surface crane to winch the aircraft directly upward was immediately rejected. A rigid crane cable cannot stretch or yield. Any wave action causing the surface recovery vessel to heave would transfer massive, instantaneous shock loads directly down the cable into the trapped airframe. Instead, the engineering plan required a localized, decoupled lifting force. A remotely operated vehicle descended to the target zone so the recovery crew could place the specialized rigging without sending divers to the deep wreck site. Using the underwater robot, the team attached specialized recovery rigging designed to support the airframe as evenly as possible while keeping the exact lifting method under operational control. The next constraint was the changing physics of compressed air. The crew incrementally inflated the attached bags, building static upward tension without creating a sudden blowout if the buried airframe released. Fully inflating the bags too early could have sent the expanding lift volume into uncontrolled acceleration, carrying the wreckage toward the surface before the team could stabilize it. The suction broke and the aircraft separated smoothly from the lake bed. From that point, the objective was steady suspension rather than speed, keeping the wreckage supported as it moved up through the water column. Once freed from the mud and stabilized, the airframe faced a second hazard, the open lake surface itself. Passing a waterlogged aluminum structure through the air-water boundary would expose it to wave slamming and shear loads capable of breaking already weakened sections. To avoid that interface, the engineering team executed a submerged towing operation. The aircraft was kept just below the surface during transit, avoiding the most punishing air and water boundary while still allowing the recovery vessel to move it toward harbor. A heavy tow cable was secured to the lift rigging, connecting the suspended wreckage to a slow-moving barge on the surface. The surface vessel proceeded at a highly restricted speed, maintaining a steady hydrodynamic profile for the suspended payload beneath it. The surrounding mass of the water column acted as a natural shock absorber, damping any sudden movements or lateral shifts during the transit. The tow route navigated across the open lake, progressing methodically toward the enclosed, calm environment of Waukegan Harbor. Inside the protective breakwaters of Waukegan Harbor, the aircraft could be lowered into shallow mud, marked with buoys, and held in a controlled staging position. The physical extraction from the deep water zone proved the validity of the submerged tow method, finalizing the highest risk phase of the handling geometry. The aircraft reached the protected waters of Waukegan Harbor, suspended beneath the surface. But how does a civilian operation legally remove a protected Navy war machine from the water? Federal law establishes a strict operational boundary for sunken military craft. The United States Navy retains perpetual ownership of all its wrecked aircraft, regardless of how long they remain submerged or who discovers them. This legal framework prevents unauthorized salvage and protects historical integrity, but it also creates a severe financial constraint. The military does not allocate active defense budgets for the retrieval of decades-old training wrecks. The decision selection for the recovery team was binary. They could leave the located airframe in the mud indefinitely, or they could engineer a private funding matrix to legally execute the extraction on behalf of the government. The logistical transition from an underwater site to a curation facility required substantial capital for heavy equipment, harbor access, and specialized personnel. Private support connected to the Taylor family and Enterprise Rent-A-Car, with reported recovery funding in the range of $250,000, supplied the necessary operating money while the Navy retained ownership, oversight, and control of the final curation destination. This cleared the path to field execution. At the harbor, the engineering focus shifted to the final vertical hoist. The recovery team positioned a heavy industrial crane on the concrete seawall of the harbor. Divers re-entered the shallow water and configured the final lift rigging so the crane could raise the aircraft slowly, with support distributed across the fragile aluminum structure. By November 30, 2009, the final harbor hoisting sequence was underway. The crane operator initiated a slow, continuous vertical pull. As the upper sections of the aircraft breached the surface of the water, a massive weight transfer occurred. The immediate loss of water displacement required the crane and the rigging to absorb the full static weight of the heavily waterlogged structure. To manage this load transition safely, the hoisting sequence paused while the aircraft hung partially out of the water, allowing trapped water and sediment to drain before the final lift. Once the internal fluid weight was sufficiently reduced, the crane completed the vertical extraction. The heavy lift equipment carried the payload through the air-water interface. The crew carefully rotated the crane boom over the seawall, then lowered the aircraft onto a waiting flatbed trailer where it was blocked and strapped down for overland transport. The Navy legally possessed the retrieved artifact, and the civilian recovery team had met the mechanical handling constraints without compromising the structure. But the moment the Hellcat left the water, the operation entered a conservation countdown. Aluminum, paint, and trapped sediment now had to be protected from uncontrolled drying, oxidation, and corrosion. The primary mechanism was rapid drying. As trapped freshwater evaporated, changing surface tension could shrink and crack preserved paint layers, pulling them away from the aluminum substrate, while wet aluminum exposed to oxygen faced aggressive surface oxidation. Immediate interventions required controlled cleaning and stabilization to remove damaging sediment without allowing the structure and surface finishes to dry too quickly. Following this initial stabilization, the exterior surfaces had to be protected from uncontrolled drying and contamination. Temporary barriers and controlled handling stabilized the artifact, allowing it to endure the logistical transfer from the harbor location to the permanent conservation facility at the National Naval Aviation Museum. At the museum, conservators assumed control of the airframe and began a structured, multi-year forensic restoration process. The first operational phase inside the facility required complete internal flushing. Fine lake silt had packed into accessible internal spaces during the aircraft's long submergence. Technicians opened accessible panels and removed sediment carefully, protecting the original structure while preparing the aircraft for long-term preservation. Following the physical extraction of the mud, the conservation team addressed the transition from wet to dry. The drying process had to be executed within a climate-controlled environment, stepping down the ambient humidity incrementally to prevent sudden warping or paint loss. Once the structural components reached a stable condition, conservators stabilized the aluminum and finishes before final restoration. Protective coatings and controlled display conditions then helped reduce future exposure to moisture and oxygen. The legal mandate from the Navy dictated that the aircraft serve as an educational artifact, requiring a high standard of historical accuracy during the restoration phase. The museum conservators faced a strict trade-off during reassembly. They had to decide how much of the operational wear should be preserved versus repairing the structural damage caused by the initial deck edge strike and the subsequent underwater burial. The team elected to stabilize the existing damage rather than masking it with extensive modern fabrication. This decision maintained the forensic integrity of the artifact. The comprehensive conservation process required 4 years of dedicated labor. In December 2013, the restored Hellcat entered public display at the National Naval Aviation Museum as a preserved record of wartime naval aviation engineering.